All right, hello again. So in this video, I'm going to go over how you can do what is called functional programming in Python. I'm going to show in particular how that can be used to simplify some of the mapping, filter, and reducing process that we talked about previously. I want to note that this is an advanced topic. You don't really need to understand or do this for basic Python programming, and really you don't need to use it at all, but it can be more useful for understanding some of the advanced work that will go on when doing data science programming or doing any other kind of doing interactive systems or doing any other kinds of more advanced programming work. But it's complicated, so I want to make sure to talk through it rather than just have you reading through the text. All right, so let's get started. All right, so the first thing we need to remember to know for talking about functional programming is to remember how functions work. So remember that a function is going to be a way of encapsulating and grouping together a set of code statements, right, of different lines of code that we can execute. So we can define a function, it takes an argument, it can then do some work and then return a value for us to be able to then use later. So functions, we should be fairly comfortable with functions and they should all feel okay, which is great because we're about to screw with them in a bit. So are you ready? Because here we go. All right, so the trick here is that functions are actually variables. Wait, what does that even mean? Okay, so the idea is that a function is a variable. A function is a value just like a list, just like an int, just like a string. It's a kind of thing. So not only is a function a set of instructions about what to do, but a function is a thing itself. So if you think of a function a little bit like a recipe, right, a series of steps that you need to follow, we can also, in Python, actually think of the recipe as like the page with all the instructions on it and then be able to do things with that page. Not just follow the steps, but actually take the page that it's on and treat that as a value, as an object, and then do more things with it. So this is very similar in some ways to a list. So remember that like we can take a list and I can declare a list and I can assign it to a variable. I can ask what type of thing it is and it'll say that it is a list. Right, if I ask what type of thing that variable is. I can take that list and that variable and assign it to another variable, right, give it a new name, basically put a new name tag on it. And then, of course, I can then use a list and use special syntax using its bracket notation to access individual elements of that list. So I sort of get, I sort of get to this superpower that lets me be able to say if I put the name of a list and put brackets after it, that lets me get a thing out of the middle of the list. It's like special syntax and list support. Functions work the same way. So I can define a function just like I defined a list, right? In this case, instead of using an assignment operator, I'm going to use the def keyword. If I then ask what kind of thing this say hello is, right? Because I've defined this thing called say hello. If I ask what kind of thing it is, then it'll say that it's not a list, it's not a string, but it's actually a function. That's the kind of thing it is, right? Say hello is a piece of paper, is like a recipe that has a bunch of instructions inside of it. In this case, the instruction is just say a print hello name, but it has a series of things we need to do, right? It's a script, a piece of actual thing that we can, you can almost imagine it's like an actual physical thing you can work with. Though it's not physical, it's all virtual. Because that is a variable, because that is a thing, right? I can take that thing and assign it to a different value. So just like I took the value inside my list and assigned it to other list, I can take the value of say hello, which is going to be this series of instructions, and I can assign that series of instructions a different name. I can assign it to a variable called greet. This is, again, it's like similar to say taking the piece of paper, the recipe with all my instructions, and I'm going to basically put a different label on the top, a different name for it. It's still the same, it's still a value, it just has a different name written around the top. So we're referring to it not as the cheesecake recipe, but as the pie recipe or something. Or not as the say hello recipe, but as the greet recipe. And then now, because that's still a recipe, and I've now given just a different name, I can use its superpower, where I can put the name of a function, right? In this case, greet is a function, because I assigned a function to greet. I can put parentheses after it, and put an argument inside of there, in order to execute and call that function. So just like with lists, when I put brackets next to them, it does this special superpower of accessing an element from the list. When I take a function and I put parentheses after it, that's activating a function's superpower, and then going through and executing and doing all the work that script tells us to do. So you can really think of these as sort of special abilities or superpowers that these different data types have, right? Lists can do special things with brackets, functions do special things with parentheses. So what this really means is that we can have functions and treat them not just as instructions, as like verbs, as things we do, but as nouns, as objects, as things that have values in and of themselves. All right, great. So these functions are variables, which means we can start using them in more interesting ways. In particular, what we can do is we can pass them as arguments into other functions. So again, think about how this works with a list. I can make my list, and then I can define a function that expects a list as an argument. And what that function will do is it will access the one-th thing from the list, right? So it'll go to my list and it'll access the thing in index 1 and then print it out, right? That's the special functions work. So I can pass in any list and it will print it out the 1th element, right? It basically gets index element 0 and index element 1. So in this case, I pass it ABC, it gets me B. We can do the same things with functions. So I can define myself a function which prints out say hello, right? That's its special work that it does. I can then define a function that will take in another function as an argument, and what it will do is just like in my list example, I access the value of the list. I will take whatever function I'm given and I will call that function. I will use its special ability by putting parentheses after it and tell it to go do its work. And in particular, I'm gonna this do with world thing is going to basically say, give me a function, and whatever function you give me, I will call and I will put world in as the argument. So I can define my function, say hello. I can specify that I want to do something to do with world, doing with that function as an argument, and then it'll call that function with world. So that when I then say do with world, say hello, it will print out hello world. All right, let me demonstrate how this works. So I've defined my say hello function, and I've got my do with world function, and I can then call them. So when I run do with world, what it's going to do is it's going to take that say hello recipe and it's going to give that to this function. So it's going to basically take that recipe and it'll go inside of the do with world. Do with world will then receive a recipe, right? Someone hands them a recipe. It will then put a new name at the top, calling it func to call. So that's the label it's giving to that recipe, and then it'll take that recipe and it will follow that recipe, plugging a world into the blank that the recipe needs. And because that recipe is say hello and its blank is this name thing, it's going to basically plug the world into that name. So that when I execute this, it then prints out my say hello. The reason that we can care about this, the reason this might be like useful at all, since it seems like we're just, we could have gotten the exact same work by just doing say hello, skipping the middleman, just doing say hello world. Oh my gosh. Sorry, I can't type this morning. We could have done the same thing by doing say hello world. The benefit to doing this kind of functional programming is it lets us start writing more generic kinds of code. So for example, I can now also define a say howdy function name that's going to print out howdy name, right? So basically we're doing another function that does the same thing. And now I can indicate that I want to both do with world argument say hello, but also do with world argument say howdy. So basically I have sort of a single function that will let me specify all the different arguments that are going to go into these other two different kinds of functions. So that effectively I can be able to say, do these two different things. I can define sort of like little sub-recipes and then have one recipe that will let me do one of those sub-things and put in different kinds of options. So you could almost, sort of an example I've used is you can imagine if you're trying to like build a recipe, design a set of functions that's going to like tell you how you want to be making some giant dinner, right? You can have like a function that might be like your create entree function that goes through all the different steps in the entree, but you can then be able to specify, but then there's like, because there's a bunch of things you have to do to actually set up your fancy dinner, but the actual entree, the instructions on how to cook the actual entree, you want to be able to sort of drop in those sets of instructions, but you want all the other sets of instructions to stay the same. So this way you can basically be able to define sort of your like make fancy dinner function and then drop in a set of instructions on how to cook the entree, and then all the other things about setting up your table and getting your dessert and all those other pieces can stay the same and work the same way. So effectively this is a way of letting us be able to define a generic set of actions, like a recipe, and then be able to use those inside of other sets of recipes. In practice, we're not going to define a lot of functions that take other functions as arguments in Python, particularly not in the kind of thing that we're doing, but understanding how that process works is going to let us be able to figure out how we can use existing functions that expect other functions as arguments. Okay, here's another example of some callback functions. So in this case, I now have a function called doTogether that actually takes in two different functions as arguments, right? So it's basically going to say that I can define two different recipes, give these two recipes to my doTogether instructions, and my doTogether instructions will then follow the first recipe and then follow the second recipe without me having to basically, and then do it at the same time without me having to call both those recipes on my own. I can basically just make the recipes and hand them over to somebody else. If I'm the master chef, I'm defining 2 recipes and handing them over to my helper chefs to go do their work. So we can define 2 different things to do. For example, pat head and rub belly. And then I can pass them both in. So I'll say, do these together, do the pat head instructions, and then do the rub belly instructions, and then print out that you did them at the same time, even though you didn't really do them simultaneously. So if you run that together, you'll see that it prints out pat your head and then rub your belly at the same time. If I reverse these arguments, right, if I do rub belly and then pat head, then what happens is now the rub belly instruction is going to be relabeled as first callback. The pat head recipe will be relabeled as second callback. So when it says do first callback, that really refers to this rub belly, and when it says do second callback, that refers to pat head. So I'm now able to effectively, by simply reversing the order of the arguments, I can reverse the order of my instructions. I now say to rub your belly and pat your head at the same time instead of the previous way. Okay, the really important thing to note here, this is the most important part of understanding how to use callback, use these sort of callback, use these functional programming ideas. This is the biggest issue that people have, and this is the most common bug that people structure with. When we're passing in a function, we need to make sure that we are passing in the variable, not the results of calling that function. So if I put in, not the results of calling that function. Sorry, I did this code here. So again, the idea is we want to make sure we specify whether we're passing in the function, not the result of calling the function. So example, if we define our function called say hello, that returns hello, if I print out what say hello is, it'll tell me that say hello is a function. If I then do say hello, say hello, and I put parentheses after it, that's now not going to refer to the recipe itself, but it's actually going to, by putting those parentheses, we're actually going to follow the recipe. We're going to bake the cake. We're going to actually do what the recipe says to do, and then the result of that function will be this returned value say hello. So if I print out the result of calling say hello, right? So I'm going to, in this case, I'm not passing in the recipe. I'm going to say, take that recipe, do that thing inside of my outer print parentheses, follow that recipe, bake that cake, and then take that cake and pass that into the printing function. So if I do that, then it actually prints out hello. So in this case, when you put parentheses after the name of a function, you're actually following that recipe, and then this work here, say hello with the parentheses, gets in effect replaced with the returned result, or replaced with whatever value that function produces. So this is the equivalent of if I just said hello in there, because that say hello is getting replaced with, that say hello parentheses is getting replaced with this returned value. So to go back up to our pat head rub belly example, if I try putting my parentheses around after rub belly, so I'm trying to not pass in the rub belly instruction, but I'm basically going to say, go ahead, rub your belly, and then take whatever rub belly returns and put that value inside here and specify that as your first callback. So if I do that, rub belly currently returns nothing. It actually returns none, right? If I just went ahead and called rub, if I wanted to just say print out the result of rub belly, right? It called rub your belly, which did that work, which prints out rub your belly, but then the result, what rub belly gets evaluated to and replaced with effectively, is the value none. So if I take my do together and I try to put in my rub belly, that's the equivalent of me saying do together and passing in none as my first callback. If I pass in none as my first callback, then when I get to this line, I'm going to now be effectively trying to write it, because first callback now means none, I'm effectively now trying to write none with parentheses after it, which you can't do because none isn't a function, you can't call it. So what ends up happening, to sort of undo, if I forget and I try to put the parentheses after the name of the function and pass in the result of the function and not the function, not the recipe itself, but I basically say, rather than giving them the instructions, the recipe, I try to give them a cake, then what's going to happen is that you're going to get an error, right? It'll print out rub your belly because, again, I'm baking this cake, I'm doing that instruction, but then I get an error where it says that none type, the result of calling that, right, what doing that work actually produced, isn't callable. I can't actually end up passing in none, and I can't end up putting none with parentheses after it. So again, this guy here is like a chef who's expecting you to give him 2 recipes. But if that chef is expecting you to give him 2 recipes, but you instead hand him a cake, he's like, this is not a set of instructions that I can follow. This thing is already built. I can't do what the cake says because the cake is already created. So the really important point here is that when you are specifying when you're passing in functions as arguments to other functions, you can't put parentheses after them. You can't call that function. You have to just give it the name of the function, the recipe that you want it to run. So we need to make sure we get rid of those parentheses, and then we can actually print our work and it all work exactly as we expect. All right, so let's talk about how this idea of this functional programming, this idea of passing functions and other functions can be used for doing mapping, filtering, reducing, because that's one of the most useful ways that we'll be able to see it. So first, here's an example of our mapping, of sort of how we did mapping previously in our previous lecture. So we would define a mapping function, for example, something that squares a number. I've got another one that does half a number. I could then have my initial list, my numbers. My mapping operation would then make my new list. I'd go through each element in my previous list. I would transform each element by calling a function and then append that function to my new list so that if I did this work, I could then, for example, square all my numbers. Now, the idea here is that if I want to square all the numbers, but I also want to have all the numbers, right? If I want to do these 2 different kinds of mappings, it involves me basically repeating a lot of code, right? I'd have to replace square with have, and I might have to do some other work. So the idea here is we want to try to generalize this process. And the way we can do that is by now using callback functions. So what we're going to do is we're going to define a function that does this kind of work for whatever list and whatever transformation I give it. So what we can then do is we can define ourselves a function, and we're going to call it map. And the map function is going to take in a transforming function, right? So we're going to pass it in a recipe, right? What do we want to do to transform our work? Do we want to square numbers? Do we want to have numbers? What are we trying to do? And then we're going to pass it in a list, whatever our list happens to be. What we'll then do is that we'll then basically do this exact same work. We'll just do it inside the function. So for whatever list they give us, we're still going to need to create a new list. We're then going to go through each element not in numbers, but now in whatever list we were given, right? We're going to take whatever list we were given, and that's the things we're going to go through. And now our transformed value is not going to be using the square function. It's going to be using whatever transforming function we're given, whatever recipe we are handed. So this is going to be the transforming function passing in that element. But otherwise, it's the exact same process, right? We're not changing any of the logic. We're just generalizing. So then instead of having to hard code in that we're going to be using the square function to map, we're now going to specify that we can use any function that we give as an argument. And it can now work with any list that we give as an argument. So now what we can do is instead of printing out the new list, we can now call our function. So we might say that the squares result might be the result of calling map using my square function as my mapping operation. Notice I'm not putting parentheses after square. I'm not calling it. I'm just specifying what recipe to use. And then the list I want to transform is numbers. And then if I print out my squares, whoop, last step, we need to make sure we return the new list so we can use that. Because again, our mapping function needs to return that value so we can use it later. Otherwise our new list is only links inside the map. So we're going to make sure we return that. But now I can do that. I can say, let's map square to numbers, and then I can print out the squares. But I'm like, oh, cool. But you know what? It turns out I don't actually want to square the numbers. I instead want to have the numbers. Well, that's cool. Now I can do the halves, can be mapping using the have function, those numbers. And then we can print out the halves. And then I can have all the numbers. So now I don't have to rewrite all of this looping work over and over again. I can effectively hide and sort of ignore that work. And all I have to worry about is writing the transformation function, which can be very simple. And it's basically saying, give me a number. How do you want to transform it? And then I can use this map function to sort of do that work. So that's the idea of this mapping function. Now, that seemed like kind of a bit of extra work for us because I had to go ahead and define the function in the first place. But it actually turns out that Python provides a map function that's built in. I don't actually have to define this function myself. So what I can do is I can actually delete this function, right? I don't need to ever declare it because it already exists. If I go to my kernel and I'm going to restart everything, so I'm going to make sure that I'm basically deleting all the variables. I'm deleting the fact that I've previously declared a map function. Sorry, edit. So hopefully this is going to run okay. So I actually don't have to. I can clear my result. I don't have to be able to specify a map function. It actually already exists. So I'm going to comment this out for a second. What I can do is I can say that I can just call the built-in map function that Python provides, saying I want to provide a transformation square and I want to pass in a list numbers. If I do that, then it prints out the squares, and what you'll notice is that this thing I got isn't actually a list. Instead, it's a map object, which is a sequence of values. This is really similar to how when I used, if I took a dictionary and I used the dot values or the dot keys function, how it didn't actually give me a list, instead it gave me a dict keys sequence. Well, map works the same way. It doesn't actually provide a list, it provides a sequence of values. But we can take that squares map, right? So this is sort of our squares map is really well produced, and we can then actually produce our list of squares by taking my squares map and transforming it into a list by using the list function. So this again, same way that we transformed our dictionary.keys or dictionary.values into a list. So if I do that, then I can get my result, which is here's my squares, producing the exact way I worked. We can sort of, to do halves, we can sort of skip the middleman, and we can say, great, let's make a list version of mapping the numbers by running them through the half function, and there's my halves. So the idea is that without me having to remember how to do mapping, without having to write a loop and remember that I need to make a new list here, and then I need to assign new values to the list, and not sort of dealing all that transformation work, all I have to worry about is that I needed to figure out what is that transformation I want to do, and I need to define a function that takes in an argument, takes in a value, and then returns the transformed version. Specify a list of things to transform, and then I can be able to very quickly be able to map those things, map from my original list through this transformation function to produce my new mapped list. So the exact same thing actually works with filter. So again, there is a built-in function, a generalized function that's built into Python that works exactly the same way. This function is called filter. It's going to take in a callback function, right, which is the filtering function. It'll then do our filtering work and makes a new list. It goes through every element in the list. It is then going to check to see if the result of calling that filter is true, right, if we should keep the item, and if so, it appends it to the list and then returns a new list where it's done. So again, this filter function is built into Python. So I'm going to comment it out. We don't actually need to define it ourselves. It already exists. So then what I can do is I can define my list of numbers. I can have my isEven filtering function, which again returns true if the number is even, if we want to keep it. And I can say that I want to filter the numbers if they're for isEven numbers, turn that into a list and print it out. And that gives me my even numbers. I can then do the same thing if I want to say the big numbers. I can say let's make a list, and we're to do that we're going to filter for big numbers. Ooh, and then of course, sorry, we got to print it out at the end. Print big numbers, and then I can print out my big numbers, which are 7. Which, if you look at my list, are 7 and 8, right? Because 2, 1, and 3 are all small. So again, that I can now, rather than having to remember how to define a filter and writing my for loop in my if statement, I can just use this built-in filter function as long as I've defined what my filtering is doing by defining these sort of individual filtering functions. So great. It's worth noting that you can compare this to, for example, to a list comprehension. So I'll show you what that might look like. So this set of using a filter function for isEven and using a list comprehension for isEven are doing exactly the same work. They're really just different approaches to doing the same kind of job. Which one you want is really sort of in many ways up to you. They can produce the same thing, but you know, this is much more Pythonic. This is sort of generally considered a better way to go. Filter is not super common, but depending on the complexity of your work, right? If this ends up being really nasty, it's possible you might want to use filtering instead. It's also then, of course, possible to combine mapping and filtering to be able to perform multiple operations on a single list. And we can do that just like we did with list comprehensions, where we sort of would have the map in one place and the filter in another place. We were able to do the same kind of thing now with making those functions more explicit using the map and filter functions. So for example, I can have my square function and my isEven function from 2 minutes ago. And what I can then do is take my numbers and I can filter them for the numbers that are even. So that's going to give me the 2, 4, and 6. So that my filtered values are now the 2, 4, and 6. I don't need to convert to a list yet because I'm not doing something with it immediately. So that filters my numbers into my filtered even numbers. I can then take those filtered even numbers and square just those guys, which will then give me my even numbers squared. So the idea is that I can first map, filter, then I can map in order to then get me the list of all the even numbers squared. And if I then print that out, I get the 2 squared to become 4, the 4 squared to become 16, and the 6 squared to become 36. That's great. This, again, might not seem like this is necessarily an improvement, but part of what we can do is I can basically take this, I can do this work. Give me a second. I'm going to clear out these comments. And I can say that, okay, so what filtered is, right, this value is really just a nickname for what filtered is even numbers are. So I can actually take that value and I'm going to copy it and I'm going to replace filtered with that value, right? So rather than defining this extra sort of middleman variable, I'm going to just say, let's map the square, let's map by squaring the filtered is even numbers. So then I can basically do this all as one line, similar to what you might do in a list comprehension. And if I print out my even squares, sorry, print out the list version of my even squares. So let me comment out that print, so we don't print it once. Then you can see that we get the exact same result. So what this lets you do is you can sort of say, like, I want to map something and then I want to filter something. If we sort of move this onto sort of their own lines, I'm going to do this just for readability, just so you can sort of see the steps that are involved here. Right, so there's sort of the end of that, and there's the end of that. So what we're basically doing is I'm saying I want to map by squaring the result of filtering, but filtering I'm going to say take is even and apply it to numbers. So part of the issue with trying to do this kind of work is that you end up figuring out what you're actually doing. You sort of have to read from the inside out, right? Where what I'm doing is I'm saying, okay, I want to do is first I'm going to start in the middle. I'm going to filter. Sorry, you can't see my fingers. I'm going to filter by grabbing the is even numbers, right? So that's the first thing I'm going to do, sort of in the middle. And then once I do that, I'm then going to square the result of calling that. So the idea is that you sort of say, first the thing I'm going to do is map, and then the next thing I was doing filtering. If I wanted to invert this, if I want to say square the numbers and then figure out what was even, right? So I want to take we'll call it squared evens. No, this is even squares. We'll call this squares. I don't know. We'll call it square evens. Sure. I can say, like, maybe I want to filter for the is even values of the result of mapping by squaring my numbers. So I can sort of do that as well in order to sort of invert this thing. So I might say list of square evens, which actually ends up being the same. Really ends up being the same thing. Right, it ends up being the same thing because I'm going to square all my values, and an odd number times odd numbers and odd numbers will produce the same thing. So that was actually less interesting. But the idea is I can reverse my behavior by simply sort of moving around what's in the middle, what's inside, and what's outside of the function. All right, so finally, let's get to the hard one. Let's talk about reduce. So again, this is where functional programming actually becomes valuable. So because map and filter can get handled by list comprehensions, we don't really need to use functional programming for them. But reduce can't be done through list comprehension. So if we want to be able to do reduce quickly and easily, we actually want to use this functional programming approach. All right, so here's how we do. So we can have so the way that reduce worked, as you can hopefully remember, is that I would define a reducer function, which is going to take in sort of a running total, an accumulation, take in some new value, and then basically take that new value and attach it to make it part of the overall accumulation, and then return that brand new accumulated value. So in this case, I have a reducer function that's linking my letters by taking some string and then using a little link, an arrow, and then attaching a new value to that. I can also have an accumulator, a reducer function that maybe does sort of reverse concatenation. So it takes the accumulation and the new value, and then it puts the new value in front of the accumulation and calls that the new accumulation, and then returns that value. So again, we could define ourselves a generalized callback that'll do this work. So we're going to have a reduce callback, a reduce function. Sorry, we're going to find, a generalized function that does this work. So we'll have a reduce function. It's going to take in what is that reducer function, right? What's that thing that's going to indicate how I should be smashing these pieces together, right? What's the joining operation that needs to occur? It'll then take in a list, and we're also going to need to pass it in the initial value so that we know what to start things at. Because if I'm trying to join together strings that I want to know that I probably want to start with an empty string. If I'm joining together numbers, I probably want to start with 0. If I'm joining together a list, I might want to start with a list. Like, it depends. We don't really know what we want to be sort of building with our reducer function. Like, we need to know what is this accumulation going to start at in order for everything to work. So the way we're going to do that is we would define our current total, started up at our initial value, right? Started at the total. We're going to start the total. We're going to go through each element of the list. We're then going to call our reducer function. So we're going to go take our reducer, right? Link letters or reverse concat. We'll then pass in whatever the current total might be, right? How far we've gotten. Attach it to, combine that element to that current total, and then take that result, whatever that callback returned, whatever my new current total is, and put it back inside my current total box, back inside my current total variable. And then once I'm all done, I can then return my whatever that current total is. So the way this can work is if I define my letters A, B, C, D, E, I can then say I want to reduce this by linking my letters, by using my link letters to actually do that accumulation. The letters list and starting it all in a blank space. And then when I print it out, I get my initial values. If I decide I want to start with a different blank value, maybe I want to start with, I don't know, with like 0, or maybe not 0. How about I want to start with Z for kicks? Then it'll put that Z as my initial value and link everything beyond that. What this also then means is if I want to then go back to my empty string, if I want to, instead of linking all my letters, if I want to reverse concat them, so I want to take every letter, and so I want to take A, B, C, D, and start combining them all into a single string, but in sort of reverse order. So I take A and put the B in front, and then put the C in front of that, and then put the D in front of that. I can do the exact same work because I've simply defined how to put one thing in front of the other. And if I do that work, and I print out my linked total again, then I now get my letters attached to in reverse order. So again, what this reduce function is letting us do is it's letting us be able to effectively do a bunch of joining kinds of operations while all we have to do is, instead of having to worry about like remembering to do all this assignment and dealing with the looping stuff, all I have to do is say that given a current accumulation, a current total, and a new value, how can I add that one new thing into it? Okay. So again, this is a reduce function that we wrote, but we don't need to use this one because there's actually a version that's built into Python. So I'm actually going to go ahead and comment it out, so it's not going to be part of our code. I'm going to then restart and clear my output to make sure that it all goes away. And we can actually use a reduce function that's built into Python. The slight trick with reduce is that unlike map and filter that are just sort of they're just public functions, or they're available inside of Python for us to use directly, with reduce, that function, as of Python 3, got moved into its own separate module because the idea is that Python was actually trying to discourage people from doing reducing work. They're like, just go ahead and use a loop, do something else for whatever reason. So if you want to go ahead and use reduce, you actually have to import it from somewhere else. We have to import it from another module. But that's fine. We know how to do that. So we're going to import it from a module called functools, which are not because they're funky tools, but because they are function tools. But that's cool sounding, right? Functools. And then we're going to import the reduce function. Once we do that, we're going to have our function reduce that, again, will take in our reducer function, our list, and our starting value. And we'll do the exact same work that we did before. So again, this is basically using our predefined function. You'll notice that because it's reduced, we don't need to transform it back into a list when we're done because we were producing a string, right? That's the thing that we ended up reducing. So I was using reverse concat to combine all my lists together, right? I could instead change this to now use my link letters in order to link all my letters together. If I want to be really clever, I could change this to being like a number, right? I can make this link a list of numbers, and I can maybe say that I want to start them all at 0. If I define myself an add function that takes in 2 numbers and returns those numbers together, then I can try to reduce my numbers. This is going to be my total. That's what I probably should just call it total. I can say I want to add in all these numbers, and I can then add up my numbers 1 through 5, which gives me 15. Which you could do the exact same thing with the sum function. And so a lot of times there's built-in reducing functions like join and sum that we talked about previously that can help do some of this work. But if I want to do things that are more complex for doing reducing, I can be able to do that work. So that's how to use map and filter and reduce using callback functions to do the same kind of thing that we were doing with list comprehensions or with just writing the equations out ourselves. So to summarize this stuff, I'd like to go through an example that I found about how to explain map, filter, and reduce using emoji. So with map, remember we can take in a list of values, like we can take in a cow, some corn, a chicken, a cow, a potato, some chicken, some corn, and map is going to run them all, each one individually through a function in order to produce a new transformed value. So if we go them all through the cooking transformation, then my cow turns into hamburger, my potato turns into french fries, my chicken turns into fried chicken, and my corn turns into popcorn. Filter then will let me take in a list of things, and I can filter for which values are true and should be kept. And again, I can just say I want to filter for whatever that filtering function that might be. In this case, it's an is vegetarian thing. So I can say that hamburgers are not vegetarian, don't keep them. Fries are, keep them. Chicken's not, don't keep it. Popcorn is, keep it. Finally, reduce is going to take in my list of things and specify what I should do in order to combine them all together. So in this case, if I take in all my food and I combine them all with an eat, they all get reduced to a single value at the end. And again, this is basically let's just describe how to do map, filter, and reduce in ways that are very explicit, because we're actually saying map, filter, and reduce. So we're just really using those words to talk about those operations. And as long as we've defined our mapping transformation, our filtering function, and our reducer function, we can write that code in a way that's actually fairly compact and easy to read and understand.